Hello, everyone. It's my pleasure to introduce our next speaker, Deniz Naz Demirel. She's my mentee. She's a student in Middle East Technical University. She will start her fourth year. And during this program, we read on ideals, varieties, and algorithms, and she will talk about some important questions that arise there. Okay, Deniz, the stage is yours. Thank you.
Thank you. Hello, everyone. As my mentor said, we will be studying three motivational problems in the book, Ideals, Varieties, and Algorithms. First, I want to emphasize that we will be working with polynomials with more than one variable over a field K. And we will be asking questions on the nature of ideals of such a polynomial ring. The first question that we ask is called the ideal description problem, and it asks whether every ideal of the polynomial ring can be finitely generated. The second question that we ask is the ideal membership problem, and it asks us to find an algorithm to decide whether a given random polynomial f in the polynomial ring is an element of the ideal generated by the polynomials f1 to fs. To be able to state the third question, I must first define what a variety is, and to be able to do so, I want you to look at figure 1. This shows the graph of the equations x cubed plus y squared minus z squared is equal to 0, and z minus x cubed is equal to 0. We can see that the zeros of these polynomials intersect in some sections here and here. And this is exactly the variety defined by these two polynomials. And in general, we say that a variety V is the common zero locus of some polynomials f1 to fs in the polynomial ring. And the variety defined by f1 to fs is denoted like this. And the third question that we ask is called solving polynomial equations, and it asks us to find an easier way to find the system of equations like this. But this is equivalent to finding the variety defined by the polynomials f1 to fs. Let's start with our first problem. This was asking whether every ideal can be finitely generated in the polynomial ring. In the single variable case, the situation is easier because we know that Kx is a principal ideal domain. In other words, all ideals of Kx are generated by a single element. As in the example, even if I try to express I by using three different polynomials, because this is the single variable case, I can always find a way to represent I using a single generator. But when we consider the situation where we have more than one variable, for example, choose 2, we deduce that Kxy is not a PID. And to show this, we can just consider the ideal I generated by the polynomials x and y. And one can easily show that this ideal cannot be generated by a single polynomial. To be able to deduce the differences between the single variable case and multivariable case, we will need some concepts. And the first one is called the monomial ordering. Some examples of monomials in the polynomial ring with three variables x, y, and z include x squared y, x, y, z, etc. Notice that these are like the terms of the polynomials, but they have coefficient 1 all the time. And then ordering, a monomial ordering is defined as follows. It is when we have n variables, it is a relation on n tuples with non-negative integer entries. The reason is that each tuple will be representing the exponent of a variable. The first condition it must satisfy is that it must be a linear ordering. This says that every two element is comparable. The second condition is that if we have that alpha is larger than beta, when I add some element gamma to both sides, the ordering must be preserved. And lastly, this must be a well ordering. This means that every subset has a minimal element. And let's consider an example. called lexicographic order, where X is prioritized over Y and Y is prioritized over Z. We say that alpha is larger than beta if the leftmost non-zero entry of alpha minus beta is positive. In other words, we are prioritizing the monomials where X has the greatest exponent. One can consider, for example, this tree tuple and this tree tuple, because X have exponent 1 here, and this is prioritized over the monomial where X has exponent 0. And in the second example, we have that the exponent of X and Y are the same, but the exponent of Z is greater here. So we get this relation. And this translates into the fact that X cubed Y squared Z to the power 4 is prioritized over X cubed Y squared Z. Let's do some exercises quickly. Let's consider a polynomial f like this and choose our monomial ordering to be LEX-ordering with X greater than Y greater than Z. Now I must check the term of the polynomial where X has the greatest exponent. That's why the leading term of f is 3x squared yz. And I say that in this case, the multi-degree of f is just the tree tuple representing this monomial. So it is 2, 1, 1. But in the LEX-ordering case where Z is prioritized, I am choosing the leading term to be the monomial where Z has the highest exponent. That's why LTF now is Z to the power 4, and the multi-degree of F is 0, 0, 4 accordingly. Next, we will need the definition of monomial ideals. A monomial ideal is simply an ideal generated by a set of monomials. And here we can see a picture. Let's consider the ideal generated by the monomials x to the power 2, y to the power 5, x to the power 3, y to the power 4, x to the power 4, y to the power 3. So everything above, everything in the shaded region, every monomial in the shaded region is within our ideal I, but everything, every monomial below the shaded region cannot be a part of our ideal I. Now we will be using our ideal I to construct another ideal of the polynomial ring called the leading term ideal. When we have a non-zero ideal and then we pick some monomial ordering to be able to choose the leading terms of polynomials, we generate a set as follows. LTI is the set of leading terms of the polynomials within the ideal I, and the ideal generated by this set is called the leading term ideal derived from the ideal I. And finally, we can answer our question by using Dixon's lemma, which does not talk about all ideals, but it says that in particular, monomial ideals are finitely generated. And by using this lemma, we obtain Hilbert's theorem, which says that all ideals are finitely generated. To our second question. This was called ideal membership problem, and it asks us to find an algorithm to decide whether some random polynomial f is in our ideal or not. Let's again check the single variable case. How do we know whether f is in some ideal I? We know that every ideal I is generated by a single element G. It is possible to find such a G. Then we say that f is an element of I if and only if the remainder of the division on f by G is 0. Or equivalently, we say that f is an element of I if and only if f is equal to G, which is the generator, times h for some h in our ring. And we were talking about remainders and division, but how did the division algorithm in Kx worked? Let's remember. When we choose our field to be real numbers, for example, and when we want to divide this polynomial by this, We first try to generate the leading term of this polynomial, but notice that here we are using secretly a monomial ordering where we prioritize the elements that has the highest x degree. And to generate x squared, we are multiplying the divisor by x. But then the polynomial left here has degree 1, but the divisor also has degree 1. This tells us that our division hasn't ended yet. So we continue to divide and we obtain a 1 here, which is non-zero. And our result thus is that x squared plus 2x plus 2 is not an element of the ideal generated by the polynomial x plus 1. Let's consider the multivariable case now. And we will be using LEX-ORDERING. And let's take f as follows. Now we will be dividing f by not a single polynomial, but two polynomials, g1 and g2. We choose some monomial ordering because that will affect our results. And let's consider the division of f by first g1 and then g2. So I will be prioritizing this divisor first. And I am considering the leading term of f, which is this, leading term of g1, which is this one. To be able to obtain this, I'm multiplying g1 by y, and I obtain the following expression. Then I check what is left here. It is minus x plus y, but no term of it is divisible by the leading terms of g1 and g2. This means that my division has ended. Now I will be dividing f by prioritizing g2. I am considering again the leading term of f and the leading term of g2 now. To be able to obtain xy squared, I'm multiplying g2 by x and I obtain this expression. And the remainder here is just 0. So we notice that the remainder differs depending on the order of the divisors. And this means that, unlike the single variable case, it is not necessarily true that for all f in our ideal, we have 0 remainder of division on f by the generators. But we want to find some similarities between the single variable and multivariable case. That's why we need the notion of GROBNER bases. When we fix a monomial ordering on our ring, and when capital G like this of an ideal I is the set of generators, then this capital G is a GROBNER basis if the leading term, the ideal generated by the leading terms of the elements of capital G is equal to the leading term ideal derived from I. But this definition is not some trivial definition because sometimes these two sets are not equal to each other. Let's consider the ideal generated by f1 and f2 as follows. I can somehow obtain minus x squared to be an element of the ideal, but the leading term of f1 is x to the power 3, and leading term of f2 is x to the power 2 times y. But clearly, minus x squared is not an element of the ideal generated by the leading terms of f1 and f2. So I say that f1 and f2 does not form a GROBNER basis for the ideal I. Let's see an important proposition about GROBNER basis. Let capital G be a GROBNER basis for an ideal I, and let f be some random polynomial in the polynomial ring. Then we say that f is an element of I if and only if the remainder of f on division by G is 0. So this is a similarity with the single variable case. And the ordering of G, the ordering of the elements of G actually is not important. At this point, we could say that we are done with our second question because we know how to determine now whether f is in an ideal I or not, but we don't know how to understand whether a given set of generator is a GROBNER basis or not, and we don't know how to construct a GROBNER basis. So our second question continues. And to be able to talk about the last 2 points I mentioned, we need the notion of S-polynomials. When we have two non-zero polynomials, f and g, and when we fix multi-degree f to be alpha and multi-degree g to be beta, we can define some gamma as follows. We define gamma where the ith entry of gamma is equal to the maximum of the ith entry of alpha and ith entry of beta for each I. Then we call x to the power gamma to be the least common multiple of leading monomials of f and g. Then the x polynomial of f and g is defined like this. Let's calculate an S polynomial together. I'm just writing the definition here. And because the highest exponent of x seen here is 4, I'm putting a 4 in the first entry for gamma, and the highest exponent seen in y in these two monomials is 2, so the second entry of gamma is 2. But notice that I'm multiplying f by x and g by 1/2 times y. So the leading terms of f and g cancel each other, and I obtain this polynomial in the end. Now, BUCHBERGE'S criterion will use S polynomials to determine whether a given basis G is a Grobner basis of I or not. It says that if I is an ideal, then a basis capital G of I is a Grobner basis if and only for all pairs I not equal to J, the remainder on division of the S polynomial defined by the pair Gi Gj by G is 0. And using BUCHBERGE'S criterion, BUCHBERGER also comes up with an algorithm to construct a Grobner basis. Let's have a non-zero ideal. Then the Grobner basis for I can be constructed as follows. First, I must find for all pairs the S polynomial defined by the pairs P and G, for all P and G in G. Then I must check the remainder on division of this S polynomials for all pairs P and G in the capital G. And if I find out that there are some, that all of them, for all of them, the remainder is 0, then by BUCHBERGE'S criterion we just stated, we are done. It is a Grobner basis. But if I find a non-zero remainder, then I add the non-zero remainder to the set G, and then I repeat what I have done. And BUCHBERGER also says that this algorithm will end in a finite number of steps.
And you have 3 minutes left.
Let's construct a Grobner basis together. But we will be using LEX-ORDERING with x greater than y greater than z. Let's consider the ideal I like this. We will be finding the S polynomial defined by f1 and f2, which is equal to x squared minus y, and the remainder of the division on S polynomial defined by f1 and f2 by f1 and f2 is itself, so it is non-zero. This means that we need to extend our set to add the non-zero remainder and call it f3. Now I will be calculating the S polynomial defined by f1 and f3, and this turns out to be equal to y squared minus 1, and the remainder of the division on this S polynomial by f1, f2, and this time f3 is again itself, it is again non-zero. So we again extend our set to include this non-zero remainder and call it f4. And one can check that this is a Grobner basis, but because it takes time, I won't do that now. Or we can use Sage to find some Grobner basis for any ideal we like. Notice that Sage here only states f4 and f3 to be in the Grobner basis. This is because f1 and f2 can be generated using f3 and f4. Now our last question was about solving polynomial equations, but this won't have a rigorous answer. We'll see why. We will study this using an example. Let's try to find the solution of this system of equations, which are polynomials over the complex field. The ideal determined by these equations is as follows. Here I'm making sure that the right-hand side remains 0. When we calculate a Grobner basis for I, but here we will be using LEX-ORDERING again, we obtain something different because the last polynomial is only in terms of z, and we know how to solve some polynomial equation like this. So we can easily determine by using the quadratic formula that the possible values of z are as follows. And then the values of x and y can be determined easily using these elements in the Grobner basis. So why did we somehow eliminate the variables x and y? Was this magic? No, it was not. And to study why this happens, one can look at the chapter 3 called the elimination theory of our book Ideals, Varieties, and Algorithms. But this was the end of my talk. Thank you for listening.